Alright, so let's continue on with ROIs. In the previous video, we discussed how to create ROIs. So now that we have some ROIs, what can we do with them? One thing we can do is we can calculate the average of the voxels inside the ROI. And we can do that with a couple different programs. Let's start with 3D MaskAv to start. So 3D MaskAv will give it the mask that has the ROI. And this is a resampled ROI to our data set. We talked about resampling in the previous video. And we'll say put it in quiet mode so we don't have too much output, because we're going to use that text output to the screen and redirect it. And we'll apply it to a particular data set. In this case, we're looking at the motion corrected data set across 3 runs of data. And this is our ROI that we're interested in, that resampled ROI that we looked at in the previous video. That greater than symbol that redirects it into EPI average 1D file, this is what that looks like. We can look at the contents of the EPI average 1D file like this with the less command, and we get a column of numbers. There will be 450 different numbers in that column. Each one is the average of the ROI at a particular time point in the EPI data set. So those are 450 numbers. It's not so much fun to look at them as 450 numbers, but we can plot that data with 1D plot. And so you can just call 1D plot with the name of the 1D text file that is a column of numbers. All 1D files are just columns of numbers. Or we can give 1D plot some options to say that we want to look at the y-axis in a particular range, and tick marks and that kind of thing. And so we have 1D plot of that data set here, and so we can see the average across time at each time point. Okay, so let's continue on. Another thing that people will often ask for is to get all the voxel values in a data set, at their XYZ values or their IJK values, and the value at the data set. So here's an example. We can call 3D mask dump. Again, we'll use the mask. The mask comes from the anatomical ROI that we've resampled into the EPI resolution, and we'll apply it onto a particular sub-brick of our analysis. This one is the reliable visual stimulus for a particular experiment, and we'll redirect with this greater than symbol into a text file. So here's an example, and this will have that XYZ, and the value will all be stored in that text file. So it's the XYZ coordinates for every single voxel in the mask. So this can be a very large text file if you've included a very large region, or you've specified the whole head or brain. Very often you won't need to do this if you're bringing it into something like MATLAB, which is kind of one of the main requests for this, but because in MATLAB you can usually bring in the data set itself and mask it there in MATLAB using one of the nifty tools there, or using AFNI's MATLAB library. But you can use this for MATLAB or for Excel or for lots of different applications, or if you just want to get a single voxel value, that's a way you can do it with 3D mask dump. And we have another program. So first this shows you take the voxel values there, but apply it onto this data set. So we're only going to take this little sliver where the ROI is here and get the voxel values within that data set there. So we have another program, 3D undump. So instead of dumping the values out, 3D undump takes the values in and creates a new data set. That one I had shown in the previous video on how to put spheres, but you can also put voxel values, ijk, or xyz values, xyz coordinates together with values to make a new data set. Another program similar to 3D MaskAv is 3D ROI Stats. So 3D ROI Stats does something a little bit different. Besides means, it also gives you medians and standard deviations, and it does it for multiple ROIs in the same data set. So here's an example. We have 3D ROI Stats. We have 3 regions in this, 3 different values in this this set of ROIs. These happen to be -1, 1, and 2. So 3D ROI Stats even works with negative ROIs. And so for each unique value of an ROI in the dataset, so each unique integer value, it tells you what's the mean of of all the voxels that have a -1, all the voxels that have a 1, and all the voxels that have a 2. So really useful way to get averages for multiple ROIs all at once. And if you have multiple sub-bricks, multiple time points, it will give you a separate row for each one. So here we're just looking at the full fstat. If you applied this onto a 3D plus time data set, it would give it to you across all the time points, all the sub-bricks. Some other tools that you can use with ROIs. 3D Mask tool. This is made to deal with ROIs. Here's an example. We're going to dilate a mask by 3 voxels, and so I'll start with the ROI we've been looking at, and I'll dilate it by 3 voxels, and I'll call the output mask tilt 3. So this is a really useful tool for doing dilation and erosion. I've only shown one example of what it can do, but lots of different functionality there. It can combine multiple ROIs. I've only put in one ROI, but if you have multiple ROIs, you can say, I want to have the intersection or union, or what fraction of all the subjects have this ROI at this voxel. I can set a fraction threshold there and save only that as my new region of interest that I'll apply as an analysis for this group. Another thing that we very often do is we'll compute an auto mask. This will usually be a starting point. We'll do it either on API data or anatomical data and say everything outside we're not interested in this at all, and everything inside we are interested in. So this generates an auto mask. Another thing we can do is we can use both 3D clusterize that we've talked about and where am I together. We can take the output from 3D clusterize, and that gives us some coordinates. We can take the center of mass output, or we could take the peak coordinate locations and analyze those with where am I. So I've clusterized the data, look to see where those clusters are. It saves it as a 1D table, these columns of numbers. I'll take those center of mass columns and I'll analyze that with where am I. Where are those columns according to atlases? So it assumes that by default that I'm in Talarex space, but I can say in the where am I command that I'm in another space. And so the input coordinates are in Talarex space here, and then we'll look at each of the coordinates and see where these fall. The Talarex daemon says one coordinate is at the left lingual gyrus, and then the next one left Brodmann area, and so it goes through all the different coordinates and it tells you where they are and what's nearby them too. Another thing you can do with Where Am I and ROIs is that you can take an ROI that you found, let's say it's a cluster of activity, where is it relative to what we know about different atlases? So this is very commonly done. I've got this atlas. This atlas is in a particular space. It may be in Talairac space or MNI space, and I want to know what regions overlap this ROI. So, according to the Talairac daemon, this anatomical ROI overlaps both the middle occipital gyrus and the middle temporal gyrus. That's in one part of the Talairac daemon. Another part of the Talairac daemon deals with the Brodmann areas. And it will go through all the different atlases and tells us how much each of the clusters or ROIs overlap different atlas regions. You will almost never have only one atlas region encompassing an ROI. So we'll see lots of different atlas regions, and different atlases will say different things about these atlas regions. So another aspect of dealing with ROIs is that if you've drawn your ROIs particularly, let's say here I've gone and drawn this ROI, and I've drawn only on the coronal slices. I draw one coronal slice, and I draw another coronal slice, and then I put them all together, and I've tried to be very careful, and then in the end I look at it in the sagittal and the axial views, and they don't look as good. And so what can I do? And this happens all the time. This happens with lots of different atlases. So people who are making atlases, we'll see an example in a second, they have created it in one direction, and for one reason or another, it's difficult to get things to be continuous across in 3D. So if you're only looking one direction, you still have to accommodate for all three directions. So this is a way to kind of regularize the regions. And so there's a method that we came up with that's modal smoothing, and it's a very simple method. We just do the statistic of the mode within a neighborhood. So here we find the most common neighborhood in a most common voxel within a 3 mm radius sphere around each of the voxels in the ROI. And so that results in this kind of data set. We make sure that it shows up as an ROI by doing the second command. And you can see that the extra bits that jut out and the extra holes, these get filled in. And so this is really useful for lots of different purposes. Let's take a look at another example. Here is the fairly well-known macrolabel atlas, the cytoarchitectonic, from the cytoarchitectonic group. This is from the macrolabel atlas that was drawn specifically for the N27 dataset. This is in the N27 space. Here's where we've transformed it to the MNI 2009 CEASE template space. So a little different, but it's still the same data, just moved over a little bit. And then we've applied various amounts of modal smoothing. So a 1 mm radius modal smooth looks like this. It starts to clean it up a little bit. Things start to jut out, remove some of the jutting. And here it's at 2 mm radius, and then here at 3 mm, and then here at 1 mm, 2 mm, 4 mm, and 8 mm. So you can see here it's very smooth, and this seems to work pretty well for this macrolabel atlas. Let's look at another example. This is also from the Icopsilus group. This is their cytoarchitectonic atlas. This is the 1.8 version of their atlas. This is their 2.2 version, so you can see it's very different in the kinds of regions that are included. And then this is with various amounts of smoothing. So 1 mm, 2 mm, 4 mm, and 8 mm. And you can see here that some things get cleaned up a lot, and some things, like these very narrow regions, disappear with larger radius modal smoothing. So you've got to be careful with this kind of modal smoothing if you carry it too far, but it does help clean up a lot of these things. This is a different kind of atlas. This wasn't drawn on one subject. It was drawn on at least 10 subjects, and then combined across the different subjects. But spatial contiguity wasn't preserved. And so some things are scattered, and there's a little bit clusters and holes. And to make it a little bit more sensible, I think this is a useful technique. For almost every atlas we've created in the AFNI group, we've done this kind of thing. From pediatric to macaque to marmoset, this is a very useful technique. Another problem that comes up with ROIs is this problem of circularity. This was a big controversy maybe 10 years ago now, in that it's also called double dipping. And the idea here is that you have two groups, for instance, and then you set a threshold and then you look at differences between these two groups, and you say these you create ROIs from the differences, and then you say their A is different from B, and then you assign a p-value on each of these, and there's a problem because we know that A is different because we just define these ROIs because they're different, and so that's called circularity. So one way around this is that we can use ROIs from other data sets. So we could use it from atlas regions, or we can generate ROIs from locator tasks or from other subjects that aren't included in the subjects that we're looking at here. So let's have an example here. Here's an example using locator tasks. So we've got some other experiment, could be in the same session, could be in a different session, but it's a different experiment. And so we can move the ROIs that we generate by clustering from one experiment and move it in from this locator task. We can move it to the task of interest, which may be a more complicated task, and we can do that using these commands here. This cat-matvec command, which combines affine transformations, and so we have to combine various affine transformations to go from the EPI of one data set into the anatomical space, and the anatomical space to the other anatomical space, and then the anatomical space to the locator space. So we have, and this can be more or less simplified or even more complicated, but this is the general idea. We can take take this combined transformation and apply it. And we want to use nearest neighbor interpolation for our ROIs, and we can move it into the space of these EPI data sets. So I put this here as reference so that you can look at that later. So there's some things to think about dealing with ROIs.